আমার মনে হয় ভাইস চ্যান্সেলর স্যার এলে তারপরে লাইভে যাওয়াটা ভালো নয় কি? লেটস ওয়েট।
অনির্বাণ,
হ্যাঁ
শুনতে পাচ্ছ?
হ্যাঁ আমি শুনতে পাচ্ছি। আমি যদি
হ্যাঁ, বলছি স্যার অসুস্থ আছেন। হ্যাঁ, so we can start on behalf of বলে দিয়েছেন, on behalf of him the inaugural address will be read out by Mongo only. Okay, so we can go ahead.
ওকে।
Sir, may I start?
Yeah, please start.
না প্রফেসর সৌরভ পালও আসেননি।
আচ্ছা, তাহলে আমরা একটু ওয়েট করি।
আমি তাহলে
একটু ওয়েট করি। মোমা একটু ওয়েট কর। হ্যাঁ,
ঠিক আছে
সৌরভ বাবু জয়েন করলে পরে স্টার্ট।
আমার তো 9টা থেকে শুরু করার কথা, উনি হয়তো আর অল্পক্ষণের মধ্যে চলে আসবেন নিশ্চয়ই। আচ্ছা, সৌরভ বাবু আমাকে হোয়াটসঅ্যাপ করেছেন, বলছেন গিভ মি দ্য লিংক। ওনাকে লিংকটা একবার কোথায়
লিংক পাঠিয়ে দিয়েছে তো,
আরেকবার পাঠিয়ে দিতে হবে।
দাঁড়াও। সুজয় বিশ্বজিৎ।
হ্যাঁ বলুন স্যার।
বিশ্বজিৎ, একটু আমাদের সৌরভ স্যারকে একটু লিংকটা আরেকবার পাঠিয়ে দিতে বলো।
সৌরভ স্যারকে?
হ্যাঁ
আচ্ছা বলছি।
সুজয়
শুনছে না মনে হয়।
আর বিশ্বজিৎ, সৌরভ স্যার জয়েন করলে পরে আমরা স্টার্ট করব।
আচ্ছা আচ্ছা
হ্যাঁ,
আরেকবার লিংকটা পাঠিয়ে দাও, আমি হোয়াটসঅ্যাপ করে দিচ্ছি যে লিংকটা অলরেডি পাঠানো হয়েছে।
আচ্ছা, সমস্যা হচ্ছে সুজয় যেখানে বসেছে সেখানে মাইক্রোফোনটা কাজ করছে না।
আচ্ছা আচ্ছা,
আমার কথা শোনা যাচ্ছে?
হ্যাঁ শোনা যাচ্ছে।
আচ্ছা, যে লিংকটা আমার কাছে আছে সেই লিংকটা আমি ফরওয়ার্ড করলে কি হবে?
গুগল মিটের লিংক?
হ্যাঁ হবে তো, হবে।
তাহলে আমি ফরওয়ার্ড করছি।
ওকে।
এই বিপুল ল্যাপটপটা নেই, বিপুল ল্যাপটপটা ও কোথায় গেল?
হ্যাঁ, তুমি দিলে অনির্বাণ, হোয়াটসঅ্যাপ করলে?
আমি ওনাকে মেল করে দিয়েছি, হোয়াটসঅ্যাপে লিখে দিচ্ছি যে মেলে দিচ্ছি।
হ্যাঁ
সুজয় তো লিংকটা পাঠিয়েছে ওনাকে, আবার উনি কি পেয়েছেন?
আমি ফোন করছি একবার।
হ্যালো বিশ্বজিৎ,
হ্যাঁ,
তুই কই বাড়িতে না এই ডিপার্টমেন্টে?
আমি কম্পিউটার সেন্টারে স্যার।
ও কম্পিউটার সেন্টারে, আচ্ছা আচ্ছা, ঠিক আছে।
আমরা সব কম্পিউটার সেন্টারে, মহেন্দ্র।
সবাই নাকি?
হ্যাঁ, আমি সজল, বিশ্বজিৎ, সুজয়, অনির্বাণ, বিশ্বাস।
আচ্ছা আচ্ছা আচ্ছা, ঠিক।
এখানে আমাদের দেখছো না কি স্লো ডিপার্টমেন্টে।
হ্যাঁ, না না, ডিপার্টমেন্টে কালকে আমি ক্লাস দিতে একদম খুব সমস্যা হয়েছে।
হ্যাঁ, ওরে বাপরে, খুব ফেড আপ।
হ্যাঁ,
ট্রেনে রিস্ক নেয়নি।
একদম খুব কালকে ক্লাসটা
খুব বাজে
মানে
অবস্থা। হ্যাঁ, কবার যে কাটলো কালকে।
সেই
কথা হলো অনির্বাণ? আনমিউট করো, আনমিউট করো।
ফোনটা রিং হয়ে গেল, আমি হোয়াটসঅ্যাপও করেছি।
আচ্ছা,
ওই যে স্পিকার, আমাদের ফার্স্ট স্পিকার জয়েন করলেই।
অনির্বাণ জয়েন করেছেন? ময়ূক জয়েন্ট। হ্যাঁ, কি
উনি
বললো
বললেন,
মা?
9টার সময় আমি 9টার মধ্যে ঢুকে যাবো।
আচ্ছা,
এখন 5 মিনিট আছে বলে আমি জাস্ট আসছি।
স্যার জয়েন করলেন উনি?
উনি উনি বললেন যে তোমার তো 9টার সময়, আমি 5 মিনিটের মধ্যে ঢুকে যাব। এখন 5 মিনিট
তাহলে
আছে।
তাহলে কি আমরা শুরু করে দেবো?
শুরু নিয়ে এলেই করবো।
পিজি স্যার শুরু করে দেবো?
বিশ্বজিৎ, উনি এলে শুরু করো।
হ্যাঁ, উনি এলে।
হ্যাঁ, উনি এলেই শুরু করো।
আমাদের ইউটিউবের লিঙ্কে কতজন আছে? ইউটিউব লিঙ্কে কতজন আছে এই মুহূর্তে? সুজয়? আচ্ছা,
পিজি স্যার, পিজি
সুজয়
স্যার,
শুনতে পাচ্ছ? সুজয়?
পিজি স্যার,
হ্যাঁ।
বলছি যে
না।
আমার সেকেন্ড স্পিকার উনি লিঙ্কটা পেয়েছেন তো?
হ্যাঁ, পেয়েছে।
আচ্ছা, ঠিক আছে।
পেয়েছে।
জানি না ওনার আবার ইন্টারনেটের কিছু ইস্যুস হলো কিনা। উনি তো বলে আমি ঢুকছি 9টার সময় তার আগে ঢুকে যাবো, 9টা তো বাজলো।
ময়ূর, গুড মর্নিং।
হ্যাঁ, গুড মর্নিং।
এ নাও, গরম চা দিয়ে গুড মর্নিং।
মর্নিং মর্নিং। পিজি স্যার, আমরা কি শুরু করে দেবো? হ্যাঁ,
ঢুকেছে, সৌরভ পাল জয়েন করেছে। ওকে, হ্যাঁ সৌরভ স্যার জয়েন করেছে। বিশ্বজিৎ, থ্যাংক ইউ অনির্বাণ, উই ক্যান স্টার্ট।
গুড মর্নিং স্যার।
মোয়া স্টার্ট।
Okay.
Good morning.
Sir, should I start?
Yes.
Yeah, please start.
Okay. Honorable Vice Chancellor Dr. Subiresh Bhattacharya, University of North Bengal. Good morning, sir, and very good morning to all other dignitaries, along with all the research scholars, students, and entire audience who have joined here today. It gives me immense pleasure to extend to you a very warm welcome to this one-day international seminar on recent trends in chemistry 2020, organized by the Department of Chemistry, University of North Bengal, in collaboration with Chemical Research Society of India, North Bengal Local Chapter, West Bengal. To begin this seminar, I would like to request my friend Shubhajit Kundu, MSc 4th semester, University of North Bengal, for the inaugural song.
Good morning, everyone. অগ্নি বীণা বাজাও তুমি কেমন করে, অগ্নি বীণা বাজাও তুমি কেমন করে, আকাশ কাঁপে তারার আলোয় গানের ভোরে, অগ্নি বীণা বাজাও তুমি কেমন করে, তেমনি করে আপন হাতে ছুলে আমার বেদনাতে, তেমনি করে আপন হাতে ছুলে আমার বেদনাতে, নূতন স্মৃতি জাগলো বুঝি জীবন পরে, অগ্নি বীণা বাজাও তুমি কেমন করে, বাজে বলেই বাজাও তুমি সেই গরবে, ও গো প্রভু আমার প্রাণে সকল সবে, বাজে বলেই বাজাও তুমি সেই গরবে, ও গো প্রভু আমার প্রাণে সকল সবে, বিষম তোমার বন্যি ঘাতে বারে বারে আমার রাতে, বিষম তোমার বন্যি ঘাতে বারে বারে আমার রাতে, জাগিয়ে দিলে নূতন তারা ব্যথায় ভোরে, অগ্নি বীণা বাজাও তুমি কেমন করে, আকাশ কাঁপে তারার আলোয় গানের ঘোরে, অগ্নি বীণা বাজাও তুমি কেমন করে। Thank you. Thank you.
Thank you, Shubhajit, for your beautiful song. I hope everybody had enjoyed it, including Professor JK, if he had joined already. So, may I now request Professor Bishwajit Sinha, Department of Chemistry, NBU, and also the convener of today's international seminar, to kindly deliver the welcome address on behalf of the organizing committee. Please, sir.
Unmute your microphone. Dr.
Okay.
Unmute.
Honorable Vice Chancellor Sir of NBU, Dr. Subiresh Bhattacharya, Head Department of Chemistry NBU and Chairperson of today's seminar, Professor Anima Mishra, Professor Pranab Ghosh, Convener, CRSI North Bengal Local Chapter, Professor M.N. Roy, Sir, Professor B.K. Maiti, distinguished invited speakers, Professor Saurabh Pal, Dr. Jung Kyung In, my dear colleagues, research scholars, and students. A very happy and healthy morning to all of you. I feel very much privileged to welcome all of you to this international seminar on recent trends in chemistry 2020, organized by our department in collaboration with CRSI North Bengal local chapter. In this tough time of COVID-19 pandemic, indeed, human life has really been in captivity for certain precautionary measures and restrictions. All these have affected our normal life as well as academic and research activities a lot. Yet, the journey of science, more specifically chemical sciences or chemistry, has not been halted. Rather, it is in full gear to combat and find a way out of the culprit virus that is COVID-19. Actually, chemistry, having a close relationship with biology, physics, and other basic sciences, has been serving the modern age and humanity since times immemorial in various issues like drug discovery, nanomedicine, material development for predefined applications, energy and environmental issues, and so on. Recently, COVID-19 has dramatically shifted and accelerated its passage. That is why today's seminar focuses mainly on recent trends in chemistry or chemical sciences. Luckily, we have two distinguished speakers amongst us, and their scientific deliberations will definitely enlighten us and extend our knowledge of the subject, and will certainly encourage the young researchers to venture into various leading issues prevailing in recent times. Hope with all your cordial participation, this seminar will be a successful one. Thanks all of you. Have a nice day ahead. Your microphone is off. Your microphone is off.
Sorry, sir. I'm really sorry, sir. Thank you very much, sir, for your kind welcome address. May I now request Professor Pranab Ghosh, Department of Chemistry, University of North Bengal, and the convener of the CRSI North Bengal local chapter to kindly say a few words. Please, sir.
Thank you, Mohammed. Respected Vice Chancellor, sir, Dr. Subiresh Bhattacharya, our guest speakers, Dr. Saurabh Pal, Professor and Director, IISER Kolkata, and Dr. Jang Kyun Im from South Korea, Session Chair, Professor Dilip Kumar Maiti, University of Calcutta, President CRSI, Professor N. Satyamurthy, Vice President, Professor Mukesh, and all the participants in the meet. A very good morning to all of you. And on behalf of CRSI North Bengal local chapter, a very warm welcome to you in our jointly organized seminar in virtual mode, Recent Trends in Chemistry 2020. At the very outset, I must mention that I really indebted to my mother department, Department of Chemistry and BU, the head of the department, and all the faculty members and research scholars to enable me to jointly organize a series of seminars in virtual mode during this pandemic situation, involving eminent speakers from abroad as well as from premier institute of our country. That also includes the one held on 12th of this month, where Nobel laureate Professor Ada Yonath from Weizmann Institute of Israel was the speaker. We are proud of having CRSI bronze medalist and council members from our department since last 10 to 15 years. Presently, we have Professor M.N. Roy and Professor Anirban Mishra as the CRSI bronze medalist, and Professor M.N. Roy is also the present council member, and Professor Anirban Mishra is the past council member. Earlier, Professor A.K. Panda, Professor B. Basu, I could remember, was the council member as well as bronze medalist. So I mean to say that we have ample human resource to develop chemistry education in this region, which is the primary objective of the CRSI local chapters. And in fact, we are very much involved in it. Today, we are very pleased to have Professor Saurabh Pal, previous President CRSI, as our guest speaker in this seminar. A stalwart in his area of research, that is theoretical chemistry. No, I should not mention Professor Pal as our guest because it will be very difficult for me to mention how many times he has visited our department. Yes, number of times he came over here. And on the other side of the coin, in Aizawl, Kolkata, we have a bunch of our MSc students pursuing their PhDs, and our student Arindam is also doing fine there as one of the faculty. So he is not our guest, but a member of our family, I feel. I am grateful to my friend, Dr. JK, doing frontier research in combination of material science and biology. Very busy person, but instantly replied positive after receiving my request. Really thankful to him. I am very pleased to get Professor Dilip Kumar Maiti will be sitting with us. He had class today from 10:30, but decided to go by the request of Pranabda. Doing so good with diversified chemistry with very good publications, and so far guided about 80 PhDs. So Professor Maiti will be with us. With this combination of speakers, we are going to enjoy a very fruitful morning session of the day. And as a consequence, I believe our students will get the golden opportunity to know about the recent trends of research in their favorite subject sitting at home. With this, I must stop here for the technical session to start. Thank you all.
Thank you very much, sir, for your kind words. Our inaugural address was supposed to be given by Honorable Chief Guest after this, but unfortunately, VC sir is not feeling well. So as per his directive, I read out the inaugural address on behalf of our Honorable VC sir. Very good morning to the distinguished speaker of the seminar, Professor Saurabh Pal, Director, Aizawl, Kolkata, and Dr. J. Im from South Korea. Session Chair, Professor Dilip Kumar Maiti, Department of Chemistry, University of Calcutta, Professor Mishra, Head of the Department of Chemistry, NBU, Professor Pranab Ghosh, Convener, CRSI North Bengal Local Chapter, all the academicians, faculty member, research scholar, and my beloved student, other dignitaries connected to this virtual event, the organizer, Department of Chemistry, NBU, and the Chemical Research Society of India, North Bengal Local Chapter. And finally, convener of the conference and the Computer Center, NBU, for their active support in organizing the meet in virtual mode. Chemistry is considered as the heart of the modern science. It is inseparably linked with biology and physics. Fundamentally, chemistry has been established as from experimental observations. But the introduction of computational chemistry since 1970s has brought a new dimension in chemical sciences as it helps to rationalize many unexplained facts. Initially, the computational chemistry was not generally considered as distinct field. However, in 1998, Walter Kohn and John Pople won the Chemistry Nobel Prize for their work on density functional theory and computational method in quantum chemistry. Since then, it has become a distinct field of research and has been widely utilized to rationalize different properties and reaction mechanism of molecules as well as materials. Moreover, computational chemistry has been an essential tool in the pharmaceutical industry to develop different therapeutics. Interestingly, it is being used to study the effectiveness of different drugs against the prevailing present pandemic. Connections made by chemistry are formed through various sub-disciplines that utilize concepts from multiple scientific disciplines. Chemistry and physics are both needed in the area of physical chemistry, nuclear chemistry, and theoretical chemistry. Chemistry and biology intersect in the areas of biochemistry, medicinal chemistry, molecular biology, chemical biology, molecular genetics, and immunochemistry. Chemistry and the earth science intersect in areas like geochemistry and hydrology. The consequences of the overlap of chemistry with biology will manifest remarkably in our study of the energy conversion process. Chemists have to formulate energy conversion devices as efficient as the living system, and probably this will be one way of understanding life. It is felt that chemistry is changing its face to a great extent due to its overlap on side with mathematics and physics and on the other side with biology. I therefore appreciate the Department of Chemistry for choosing the theme of the international seminar in virtual mode as Recent Trends in Chemistry 2020. I believe the seminar has been intended to highlight the recent advances in chemical and material science, including recent advances in computational chemistry, as well as synthetic chemistry for developing new molecules, which will have potential application as transporter across the cell membrane. I must appreciate the joint venture of Department of Chemistry, NBU, and the CRSI North Bengal local chapters for arrangement of a series of virtual mode of seminars in the pandemic situation, which would definitely compensate the losses students are having during this year. I wish a grand success of the seminar. Thank you very much, sir, for your thought-provoking address. It set a perfect platform for our speakers to deliver their presentation in their specific areas. Now, moving forward, we are going to start our first technical session of the day. Our first speaker for today's seminar is Dr. Saurabh Pal, Professor and Director of IISER Kolkata. May I now humbly request Professor Anirban Mishra, Head, Department of Chemistry, and also the Chairman of the Organizing Committee, University of North Bengal, to kindly chair the session. Please, sir.
Thank you, Mohan. Good morning to you all. Good morning, our honorable speaker, Mr. Saurabh Pal. Nice to see you in the morning. So, we had the inaugural session. Now we have plenty of audience, few in the Google Meet and few others joining us in the YouTube link. I hope today's program will be a grand success with the first speaker as Professor Saurabh Pal, who doesn't need any introduction to the audience, at least those who are present in the Google Meet. But those who are there in the YouTube link, many of them are our young students of MSc first year and second year. So for them, I'll just say very briefly about the achievements and the work area of Professor Pal. So Professor Pal has done his master's degree, integrated master's degree in chemistry from IIT Kanpur. Then he pursued his PhD in IACS, Indian Association for the Cultivation of Science, Kolkata, with none other than a stalwart in the field of theoretical chemistry, Professor Debashish Mukherjee. Then, at a very young age, he joined NCL Pune as a scientist, and in between, he had pursued his postdoctoral research in Florida State University with Professor Ruth Bartlett, and then subsequently in University of Heidelberg with Professor Lance Sederbaum. So he has developed many new formalism, theoretical formalism, and made phenomenal contribution in the field of couple cluster theory, particularly response approach to the response approach in the couple cluster method, multi-reference couple cluster method, and that's his theoretical side of work. And the application side also, he has done work in DFT and design of materials, design of new magnetic systems, and so on. He has received many, he has published numerous papers in all big journals. He has all kinds of, he is one of the most well-decorated scientists in India at present. And not only he is a theoretician, he is regarded as the stalwart in the whole domain of chemistry. He has received Sankeshwara Bhattakar Award. He is fellow of all the National Science Academies. He is a policymaker in the different bodies in the country, and he has served as director of NCL Pune. He is currently serving as the director of IISER Kolkata, and the IISER Kolkata under his directorship is Kumari Singh, that we all know. And we are proud of him, and I request our beloved Saurabh to start today's discussion.
Thank you, Anirban. Am I audible?
Yes, sir.
Yeah. The screen can be seen. Hello.
You have to start presentation.
No, is the presentation? I'm already on the screen. Can you see the presentation?
No, we cannot see, sir.
We cannot see.
Okay, let me see what is the problem then. Okay, let me go back and do. Can you see the screen?
Not yet. You take the present now option. Turn on the, it's not working on the right hand.
I had done this already. I think maybe you have to give some rights or turn on captions. No, turn on caption is not. Present now is already clicked.
But it's not working.
So maybe, sir, you can full screen your presentation file.
No. Full screen is not a problem. You have to first see the screen, right?
I think what Honorable Mr. is saying, can you clarify why it's not happening? Can you,
Huh? You are not able to see the screen because I'm not even getting present now.
you are not getting present now.
You have to share the screen.
Can our computer center people can give some tips?
No, it should have worked. Actually, it should have worked. I'm surprised.
Sir, can you please send your PPT by mail to us so that we can
Yeah, I'll do that.
That can be sent.
Let me just try one more time.
Right. Otherwise, you can send through email to us.
Yeah.
We'll operate and you will speak.
Can you see it now?
No.
Sir.
No. There is some problem. Okay, I will send it to you. Which address I should send?
Anirban, you take the thing. Anirban, you receive the mail.
Send me in my email, sujayrana@nbu.ac.in.
Suya Rana.
Suya Rana.
Okay. Send your mail ID to sir.
Yes, sir. Yeah. So already actually, I have sent him the mail already.
That's okay.
Otherwise, you write it in the chat box.
Yeah.
You write it on the chat box, sir will see and say we'll send it to you.
It's only 21 megabyte. Let me see if it goes. Otherwise, I'll send from Gmail.
Yes, sujoy@nbu.ac.in.
No, that is okay. I got your email. No problem.
Okay, Gmail also I am giving.
Maybe I should have gone from Google Chrome.
Oh, yes.
Yeah, Google Chrome.
Yeah, probably I'm joining for the Mozilla. That's the problem. Can I just log out?
Yeah, I think that.
Yeah. I think Google Chrome will allow the pops up.
Yeah, better would be Google Chrome, sir.
So you once log out and then come back.
Has Sujay Rana got it? Are you able to see? Hello.
Sujoy, check your email. Sujoy. Sir,
Are you able to see the screen now?
no, sir.
No.
Sir, Surya has received your mail and he is preparing for presentation.
Okay. Okay. This cannot be seen yet.
No, sir.
He is doing, sir. He is doing.
All right. All right. Okay. Fine.
Yes.
Okay. Sorry.
I have shared you the PPT.
Yeah. Yeah. Okay.
Yes, sir. Please go
Sorry.
ahead. Yeah.
Yeah. You are able to hear me, right? Yeah. Okay.
Yeah.
Sorry. Sorry for the technical hitch-up. I'm surprised why it happened because even in browser, I'm teaching all the time in the Google Meet and sharing screen. But that is in the Mac, so I don't know. There is a problem with the Windows. Anyway, so let me start. I have probably changed the title a little bit to make it more general, and I will be talking on the modeling of biomolecules and materials, theory and applications. First of all, I thank North Bengal University for inviting me to this webinar. I'm sorry that the date is wrongly written, 15th October. It's actually 16th. I have been working at ICER Kolkata for now little more than 3 years as a director, but previously I was in National Chemical Lab, and in between I also was at IIT Bombay for a few years. I just retired, in fact, in this month from IIT Bombay. So I am becoming an expert. I always tell I'm becoming an expert in retirements. So I think I will retire from many more places probably. Visiting, I'm also working in Ashoka University as a visiting professor. So I'm very happy to be invited in this international seminar today and share my thoughts. Share my thoughts. So please go to the next one. Go to the next one. Can I change? Yeah.
Yes.
Sujoy, please mute yourself.
Yes.
Yes. So these are just I think the full screen is not coming, but it's okay. These are the 3 cities in which I lived. So I'll quickly run through some of the initial slides because go to the next slide. Yeah, so I'm working in ICER. For those who do not know about ICER, ICERs are research and innovation universities. They are basically institutes, but they are research institutes. And we have 7 of them. Kolkata and Pune came in the beginning in 2006, and I have been fortunately involved with the ICER. Even before ICER started, in 2004, I was in the implementation committee of the ICERs. So actually, it was very good to know about ICERs when I was in NCL. I did not realize that I would actually come to ICER eventually. But I was involved with ICER Pune as a visiting professor right from its inception. So then, of course, after Pune and Kolkata came Mohali, then Trivandrum and Bhopal in the same year, 2008, and then later Tirupati in 2015 and Berhampur in 2016. Can you go to the next slide? So this is our campus, which is of 201 acres land. For those who have come to the campus, it's quite green and picturesque. We are now out of the first phase of construction. And that is very good because we can now get funding, you can apply for funding for the next phase of construction. I think it's very important that the construction and the campus building must continue as we continue to grow. So next. Next slide, yes. So the chemistry, that other slide I just missed to say that we have been consistently ranked well in the NIRF ranking, but that is beside the point. NIRF as well as in the Nature Index ranking. The Nature Index ranking, particularly in chemistry, we are among the top 2 or 3 institutions in the country. All right, so since it's a chemistry audience and it is done under the CRSI local chapter, I thank the CRSI local chapter as well. I should say a little bit about where is the chemistry education today and the hierarchy of chemistry education. Very importantly, something that I have been emphasizing at IISER, integration of research with education. Very often research and education have not been understood properly. Many universities, like even North Bengal University, has a very good research base, but all the universities do not have such an integrated research along with education. COVID-19, of course, has proved severe challenges, but has also given opportunities in terms of chemistry education. The online learning is something that will probably stay even beyond the COVID. Can you go to the next slide? So why do you do science? And I think for general, I will not talk about it. It's for a general audience that science provides basic expertise and science gives lots of options. Academic research, teaching, industrial research, and many alternative science careers. But very importantly, I and probably many others took up science because it fulfills the mind, because it's a very satisfying job. Not that the science was a very paying job, as it is probably today. Today, I think most of the education, people who are in the education and science labs, it's quite reasonably rewarding compared to the Indian standards. But certainly when we started, it was not a very rewarding job, but we did because it gives you freedom and fulfillment of mind. Can you go to the next slide? So there are opportunities in science, which I told, academic institutions like IITs, IISERs, NITs, universities, colleges. Then there are research laboratories, which are also becoming academic institutions like CSIR, IISc, TIFR, cultivation of science, etc. Then there are mission-driven labs like atomic energy. Even they have now Homi Bhabha National Institute, HBNI, under which they are actually giving degree. Then there is a space, defense. Education is becoming very important theme, even in the research labs, even in mission-driven research, like Department of Atomic Energy and so on. Of course, then you can do industry R&D, which I talked about, and then entrepreneurship in terms of startup. But what we really need is a deep innovation, which means innovations based on high scientific knowledge and discoveries. Let's go to the next slide. So the fundamental science, of course, is known to be curiosity-driven, but it's not always curiosity-driven. There are science which are done by necessity, like Archimedes. Very often you know Archimedes' discovery because King Hero challenged him to find out if the goldsmith is cheating. There are accidental discoveries. Of course, many of you know the discovery of urea, which was an accident, the discovery of microorganism, which is also by an accident. And of course, curiosity-driven, which is very famously quoted as one that Isaac Newton did. But I think there are many who have done curiosity-driven. Fundamental science is basically known as a curiosity-driven, but not always. There are examples of Fred Kekulé finding it because he had some thoughts, maybe dreams. It's not very clear, that part. But somehow there are many other ways that one can actually do fundamental science, to discoveries. Can you go to the next slide? But what is important is that when you do fundamental understanding, today it is very important to do translation. So at the same time, you have a y-axis quest for fundamental understanding, and on the x-axis, it's a consideration of use. So it's very important to realize what you need to do is to go to this right top quadrant, which is high science, high application, and this would be called use-inspired basic research. This is actually pure basic research, which is Bohr quadrant, and then you have the Edison quadrant, which is the high application and low basic research. So I think this is very important to realize that the demand of today is basically what is given by the Louis Pasteur problem. Can we go to the next slide? There are, of course, Nobel laureates who are Indian and Indian origin. Today, we are trying to bring all Indian origin scientists under one platform. In fact, many of you know that there is a summit that Prime Minister's office is conducting through DRDO, which is called the Vaibhav Summit. The Vaibhav Summit essentially is a summit where the Indian origin people, the entire Indian diaspora, meets to discuss what can be done for India. And I think it's about 22 or 23 verticals of different scientific verticals in which discussions are going on. In fact, I'm deeply connected to a vertical called computational science, under which there is a horizontal called computational natural science. In fact, just last 2-3 days, we had chemistry, physics, material science, computational material science. So IISER Kolkata is actually leading that particular segment. So it's very important to realize that even in the Indian origin, there are only 4 Nobel laureates in science, and that's not enough. So it's important that we have more Nobel laureates. How to create such discoveries is, of course, a very big issue. Obviously, Sir C.V. Raman is the only one who can claim to have done the discovery from within India. Let's go to the next slide. So we have to catch up in the science, and there are catching up in which you have to look at education, look at research, look at technology. But we have to realize that our ancient Indian science was not bad. So one has to think beyond that and rationally. Inventions like zero, number theory, Ayurveda, geometry, algebra, even computer algorithms existed long back, even before the algorithm started. Formally, I have seen even books in which these exist. Actually, Professor B.M. Dev has written a very nice book on, I think, the peacock, Indian peacock or something. It was just captured about the traditional Indian science. In fact, I very remember the old Indian science, which had very strong base, and somehow we lost it in the middle. Can we go to the next slide? So the hierarchy of, this is basically the hierarchy of science education. There is no instinctive knowledge in chemistry to start with. And chemistry actually looks very complex at the school level. Whereas physics and biology are somehow subjects which are easy to feel in everyday life. Chemistry has kind of proceeded by transfer of knowledge, and that has been the most popular process. In fact, there are considerable evidence of both the learners failing to make sense of teaching and the students developing alternative conceptions of the material presented to them. So chemistry is very complex because we don't feel atoms and molecules, whereas physics we see, at least the classical mechanics, electrodynamics, many of the physics we see, so is the biology. But the chemistry has we see most of the students preferring to go to physics and biology. Can we go to the next slide? Yes. Okay. However, we realize that the chemistry is a central science, and there is a hierarchy of sciences building upon each other. Like a very traditional way of thinking is that the physics is built on mathematics, chemistry is built on physics, biology on chemistry, psychology on biology. But obviously, this is a very traditional thinking. The relations are not equivalent. For example, maths is, of course, a tool which is heavily used in physics, but it is also used in many other subjects like chemistry, biology, etc. There are large parts of biology that also make direct and indirect applications of chemistry. Similarly, physics today also relies on chemistry. So this standard hierarchy has broken down. Same thing with the psychology. So the problem today is that the science is becoming more and more interdisciplinary, because previously students could think of choosing only physics and mathematics or chemistry and biology and so on. But today it is not possible because of the interdisciplinary way that the science has developed. Can you go to the next slide? Chemistry, however, has been driven by structures, but today it has to be driven more by functions. And I think that is a very important part to realize. Can you go to the next slide? The real problem in chemistry education has been to break the traditional barriers of a discipline-based chemistry, like organic, inorganic, physical, biochemistry, etc. In fact, it's very hard to imagine that the physical chemists are working within the same paradigm as the organic chemists are working. So the paradigm itself looks simply different. So basically the synthetic chemistry paradigm has been different from the physical chemistry paradigm, though the connections people can make today. So that is how that's what I'm going to come to, how computational chemistry has been able to integrate different science. Yeah, can you go to the next slide? So chemistry today has been driven by emerging trends in research, technology, as well as societal needs. Can you go to the next slide? I believe, and since I'm actually addressing a university, I must propagate that the history of science must be put as a curriculum. You know, history of how Archimedes discovered, Newton discovered, history of Einstein, of course, Avogadro, and the entire evolution of chemistry, which I've just put a few of the modern chemistry, starting from oxygen, atomic theory, etc., etc. Bohr theory, and of course, chemical bonds, electrons, that's very important. And one has to realize that the electrons were discovered almost 100 years after the batteries were discovered. Batteries were discovered in 1800, whereas electrons were discovered in 1897. So today we, of course, attribute conductivity to the motion of electrons. But remember, the electrons were discovered about 100 years after batteries. So that's very interesting, fascinating science, the history of science that we need to teach. In fact, we talked of the theoretical chemistry Nobel Prizes. It's very hard to say which is theoretical chemistry Nobel Prize. In fact, J.J. Thomson got Nobel Prize in 1906 for the discovery of electrons. Rutherford in 1908, Niels Bohr in 1922, I think, and so on. So there have been many of these people actually got theoretical chemistry Nobel Prize, though we probably would think Fukui and Hoffman sharing the Nobel Prize in 1981 as a more modern theoretical chemistry. And then, of course, you know, Pople and so on, the Gaussian and Pople and Kohn. But I think the theoretical chemistry had a long tradition in between Hitler, London, so many people, Clementi, so many people have worked in theoretical chemistry. The history of theoretical chemistry itself is very, very fascinating. Can you go to the next slide? So the future challenges of chemistry are in the following sectors. It's very hard to write down all the sectors, but this is my own list. Renewable energy, sustainable resources, energy efficient processes, environment friendly processes, affordable healthcare, cultivation of farms, technologically enabled defense systems. In many of these, chemistry is going to play a very important role. Can you go to the next slide? We have to move a little faster in the slides. And within the renewable energy, we have, of course, sustainable resources, and they are solar, wind energy, fuel cell, bio-waste to alcohols and fuels. Hydrogen is a very important part of the renewable energy, nuclear energy, carbon dioxide into fuel. That's very important. So can you go to the next slide? In terms of challenges of COVID-19, we have to do research to combat this. Prediction of environment and protection of environment and climate is going to become a very important part when we go for the post-COVID-19. But a very important part will be technological innovation of doing industry. So how will the chemistry position itself into this new post-new normal, which what we call new normal? Of course, there will be more digitalization, and education, of course, will become online, which should be anytime, anywhere, anyone, anything. So that's very important. It has opened up large opportunities because we can now engage teachers from anywhere in the world. I think that's very important. Let's go to the next slide. So in the new normal, there'll be opportunities to have innovative solutions and protect climate and environment. Thrust of research in virology, of course, in pharma. Smart materials to make life easy. In fact, when you do digitalization, smart materials is again going to come. And of course, how do you communicate in an era where the physical meetings are going to be taking place less and less? Innovation in education. How do you conduct the laboratories? I think all universities, institutions are looking at how do you convert laboratories. So these are all about the chemistry education that I'm talking right now. Can you go to the next slide? So I will now change gear and quickly come to what the computational science has done in terms of integration of different science. It is not just chemistry, not just organic, inorganic. I'm talking about not computational chemistry, but computational science. It's a very important arm in a triangle to solve problems. So the solution will come from an arm: theory, experiment, computation. So I think these three things together are going to provide a solution. Can you come to the next slide? The fact that the computational science is going to become very important was actually given by Quetelet in 1828. And it said the more progress physical sciences make, the more they tend to enter the domain of mathematics, which is the kind of center to which they all converge. We may even judge the degree of perfection to which a science has arrived by the facility with which it may be submitted to calculation. So you can see, even 200 years back, people thought of the importance of computational science, the mathematics. At that time, of course, it was in the domain of mathematics. Can you go to the next slide? However, look at the next quotation from Comte. I think that's missing here. A. Comte in 1830, 2 years after, and this is in the context of chemistry, which is very relevant. Every attempt to employ mathematical methods in the study of chemical questions must be considered profoundly irrational and contrary to the spirit of chemistry. If mathematical analysis should ever hold a prominent place in chemistry, an aberration which is happily almost impossible, it would occasion a rapid and widespread degeneration of that science. So you can imagine what was the feeling 2 years after in the context of chemistry. And I think it's the same as biology. It took a long time to understand that mathematics and computation has a big role in chemistry. In fact, today biologists are now only realizing. Chemists probably realized a little bit earlier. Can you go to the next slide? Yes. So using theory, computers, and fast algorithms, we solve complex equations from the theory, predict in computer structure and properties, reaction between the molecules, how fast the reaction takes place, dynamics of evolution, modeling of new materials and drug designing, biological activity. And today, what is going to become very important is not necessarily just physics-based approaches, but mathematical tools of artificial intelligence and machine learning, just to look at big data and try to make sense of it. I think everywhere they're talking of artificial, even computational chemistry is going to get revolutionized because of AI and ML. Can you go to the next slide? So of course, theoretical chemistry started even before modern quantum chemistry. And I don't know what you call theoretical chemistry. I would say even J.J. Thomson's discovery of electrons is a part of theoretical chemistry. But very importantly, G.N. Lewis, I have to mention because G.N. Lewis did not get any Nobel Prize. But it almost started from G.N. Lewis because he started first talking of the chemical bond through octet, and his very famous paper, The Atom and the Molecule, in Journal of American Chemical Society, 1916, actually set the tone for the chemical bond. Can you go to the next slide? Then came lots of methods. Of course, quantum mechanics, then there are classical simulations, and today what we have is a plethora of methods, which is called multi-scale methods for different length scale. So we have at small length scale quantum mechanics, or even approximate quantum mechanics. It could be DFT, could be anything. And at a larger length scale, we will have a classical approach like molecular mechanics. And you can actually combine both of them. In fact, there is a Nobel Prize in 2013, which was shared by Arya Varsel, Karplas, and one more person. I think I'm just not getting the name. But there are three people who actually, I think Michel Levitt. So they shared the Nobel Prize in 2013 for the discovery of PMMM method. So it basically allows quantum mechanics and classical approach to be used together. Then, of course, there is at a higher length scale, you have coarse-grained simulation, and this is applied for polymers, for example, and even larger systems, and eventually it joins to engineering simulation. And that's very important to realize that how to model approximations at even larger length scale. The really very interesting part would be coarse-grained simulation, which are important for biomolecules. Can you go to the next slide? Of course, the very fact that the quantum mechanics can go to the classical and meso was actually highlighted long back by Niels Bohr. If you remember Bohr's correspondence principle, he said the limit h going to 0, quantum principles go over to the classical. So as you go from atoms, molecules, cluster, nano, and bulk, that's classical. So it's a bottom-up approach. The question is, today we can choose theory depending on our system. But the key question remains, where does quantum mechanics stop and you can use classical mechanics. The real issue is that quantum mechanics is there everywhere. The point is, when the system becomes very large, you don't need to invest time to solve quantum mechanics. You can actually just simply solve it with the classical limit, and the results are quite good. You don't need to do quantum mechanics. But which is that limit of size? That is very important. Many people think it's nanomaterials, and that is a great point of debate among the theoreticians. Can you come to the next slide? So this is the box which is today available to us. And I call it horses for the courses, which means depending on the course, you put your horse. So you have different time scales, different length scale, and you have different methods, like ab initio methods for small time and length scale. Then you have atomistic simulation for proteins and so on, which I call molecular simulation. Then you have mesoscale simulation. I talked about it. And then macro scale simulation, finite element, Brownian dynamics. So many methods are there. In fact, ironically, this of course developed very early because this is classical mechanics. And the second thing to be developed was actually ab initio methods before these intermediate scales were developed. But today we have theory for all scales. Can you go to the next slide? And that makes it very easy. I must talk a little bit about mixing this length scale. So it is not using just quantum mechanics or classical mechanics. Today you can use what I call QMMM method, in which you do quantum mechanics at a place where you require quantum mechanics, and then there is a boundary which is given by the green, and then the molecular mechanics. So the boundary between blue and the green is the interface, and that is where you have to do some tailoring. And I think I'll not go into the details. But it means that if an interaction is taking place here, cut this zone as a quantum mechanics, maybe a few angstrom from the interaction side, quantum mechanics, then an interface zone, and a very large systems like membrane, you can't do quantum mechanics. So this can be classical mechanics because it's a very long range interaction. So this is very important. The chemically active part to be treated by quantum mechanics, then there is an interface, and then there is a large environment, which is basically classical force field. So can you go to the next slide? Within the quantum mechanics, when you come to the materials, the choice is actually not the solution of the Schrodinger equation. The choice is a density functional theory, which essentially says that the energy can be expressed in terms of only three-dimensional electron density. Because it is always three-dimensional, it is unimportant how big is the system, and that is how the DFT, or the density functional theory, became very popular. However, while this is true that the energy can be expressed, it is impossible to find an exact expression till today. The major problem is to find an expression for the exchange and the correlation functionals. Mixing with the Hartree-Fock exchange to get better results is one option. That's a Minnesota functional. One has to worry about how to include dispersion in this functional and then get the basis sets, atom-centered or periodic basis set, depending on the need and the model. Can you go to the next slide? I just wanted to tell you what is the problem of density functional theory by one slide only, although I'm going to present some results for the materials, which is going to be by density functional theory. But just want to tell you, these are the enthalpy changes are very simple reactions, as you can see here on the left-hand side. These are the experimental numbers in kilojoules per mole. This is a very accurate calculation by solution of the Schrodinger equation, which is called the couple cluster, singles, doubles with partial triples. And you can see that these numbers are just so good with this experiment. It's absolutely very good. I mean, this is quite good. If you look at G2, which is a method by Popel and co-workers, which is the combination of NP2 and what they call quadratic CI, singles, doubles, and triples. Again, I will not go into the details. It's also pretty good. I mean, this is as good as couple cluster, almost. Though I would say couple cluster behaves even better. But look at Hartree-Fock, it is pretty bad. I mean, you don't even get the sign right. Of course, Hartree-Fock is very bad. So you require electron correlation. That's for clear. But look at DFT, which also includes electron correlation, but in a manner which is not understandable. So you can see that some numbers are very good, like this. This is also reasonable. But you look at this number, it's not so good. This is again very good. This number, not so good. This is again not so good. So you can see up and down. The DFT is reasonably reliable, but you can't always trust. That's the message that I want to give while we continue to work on DFT. Can you go to the next slide? Yeah, can you go to the next slide? I think this is the same. All right. So when you go to atoms, molecules, and cluster to solids, remember we have to use for the atoms and molecules, we use normal quantum chemistry. But the important thing to realize that we use what is called the atom-centered Gaussian basis sets, even for clusters. Electron correlation is, of course, very important. And we use several ab initio methods, which is solution of the Schrodinger equation, like MP2, couple cluster, Gauss SCF, etc. We can also use DFT. When you come to larger solids, then of course, particularly if it is periodic solid, then you don't use atom-centered basis set, but you use what are called the periodic basis sets. But due to the complexity of the problem, very often you use what is called the density functional theory. So DFT is often the method of choice. Cluster chemistry becomes a link to the catalysis. It is very important. And some of the programs that I'm going to do is from the clusters of atoms. And the clusters become the link to the catalysis, because you understand how a cluster can represent a surface and how a reaction can take place. So design of catalyst very often is done by cluster chemistry, where I can use DFT, where I can use ab initio methods. But more often than not, I will be using the DFT. Can we go to the next slide? I will skip this slide just to say that if you want to do molecular dynamics, then the nuclear movement you do by classical mechanics, by Newton's law, and you can do complete force field, whereas electrons are not there, only atom-atom interaction, and that is called the classical molecular dynamics. Can you go to the next slide? And then, of course, if you allow nuclei to move by Newton's law, but electrons are considered in terms of quantum mechanics, they will call the ab initio MD. So can you go to the next slide? So that's the ab initio MD, where you mix classical movement of electrons with the nuclei with the electrons being described by quantum mechanics. So this is really a mixed representation. And of course, there is another dynamics which is very difficult, where nuclei and electrons both move quantum mechanics. So you actually solve a nuclear Schrodinger equation. Very few people, even in India, are doing, but there are few at ISAs like Satyajit Adhikari, then Susanta Mahapatra at the University of Hyderabad. There are people in IIT Guwahati who are doing the full quantum molecular dynamics. It's very hard to do that. Quantum dynamics, you don't call it molecular dynamics in that case. Can you go to the next slide? So I just want to tell, can you put this, there is an animation here. For the design of catalyst, I have to say that there are a lot of things which you have to worry about. And many of these can be done today manually and in very, very different way, like selection of metal, pre-catalyst, reaction method, ligand selection of coordinating sites with ligands, solvent selection, reagent, substrate, need of additives, and so on, co-catalyst. Many of these, so this is a large number of combinations that you have got. And this is where I said, can you go to the next slide? This is where I said you require the artificial intelligence and machine learning. So this is where machine learning can become very important. What we will show are some examples from my own research on metal cluster, particularly gold and silver clusters for oxidation reaction. In fact, I can tell you clusters are very exciting. Like, for example, one of the important things that we did, and I'm just going to go through very quickly, that the gold cluster, and these are all experimentally synthesized in gas phase, I can tell you. These are gas phase cluster AU8, that's inert. But if you just dope AU8 by one silicon monodope, Si87, then it becomes catalytically active. Pristine gold cage, AU18, activated by metal inside the cage. It's very important to realize that there is a pristine gold cage, AU18, but that is not very active. But if you put a metal inside the cage, it becomes active. Similarly, if you take some gold or silver clusters, small clusters, their activity gets enhanced if you put a hydrogen atom chemisorption. Now, these are clusters which are actually experimentally synthesized, very difficult to synthesize. So very, very powerful experiments have been done where people can synthesize. We also looked at aluminum cluster. I'll just quickly say that for the dinitrogen activation. Can we go to the next slide? So just yes. So this is, for example, AU18 gold cage, a very good reaction pathway that we have drawn by CO oxidation. This we published about six years before in Journal of Physical Chemistry. So this is CO oxygen with the AU18, and it's a very detailed calculation where you looked at the intermediate, transition state, and then finally the product. So it's a very detailed reaction mechanism for where we can get the barriers. And if you go to the next slide, if you point out the barriers of 0.71 and 0.45 or 2 barriers, you can look at the same barriers, how quickly can you make one more thing? There's an animation. So can you click again? Yes. So you can see, sorry, go back. Yeah. So you can see if you have a sodium, potassium, magnesium, or calcium in the dope AU18 gold cage, how the reaction gets facilitated. With the barriers all get dropped down, so the CO oxidation reaction will go much faster. Now, these kind of clusters are possible to synthesize today. AU18, it may be possible to put metals inside the cluster. I think experimentalists have to also synthesize. So today we are giving leads of what kind of clusters can be very good catalysis, like silicon AU7, I told you. Can you go to the next slide? Another important work that I talked of, hydrogen chemisorption. So again, it's a CO oxidation reaction. If you look at just AU6 and AU8, again, these are experimentally synthesizable. Look at the bond length. It first gets to the oxygen bond, and then it gets elongated. So if you look at the binding energy of oxygen, it's 0.25 eV. Oxygen bond length is 1.23 eV. If you do the same AU6 with hydrogen, then you can see the binding energy goes to 1.30. Now the oxygen is getting actually activated. It goes to 1.32. And the same story with AU8. So I'm just showing the story. It is not very good, but as soon as you put AU8 hydrogen, it becomes elongated. Activation takes place. If you look at the barrier, it's even more dramatic. For AU6, it is 0.721 eV. AU8, it is 1.193 eV. But moment you put hydrogen chemisorption, this becomes almost barrierless, 0.721, and this becomes 0.360. So which means the reaction will now go very fast. And that's a very interesting thing. Just you have to put a hydrogen atom onto these clusters. And fortunately, people are able to synthesize such clusters. Can we go to the next slide? We have been also working a little bit on the hydrogen storage. In fact, we have worked a lot on metal cluster. I must also talk about the aluminum cluster, which I skipped for the lack of time. We have actually come up with a very good catalyst, which is a graphene. And on graphene, we put boron nitride, BN molecule, doped graphene, and then put aluminum cluster. And this we have seen can activate carbon halide bond. It can activate dinitrogen activation. It can activate oxygen activation. So many of the activation can do. And I hope one day it can be synthesized. With aluminum is very reactive, as you know. So even to put aluminum clusters on a BN doped graphene is not going to be very easy to synthesize. But our prediction is that if one can synthesize, it will be a very good material for many other activations. So let me go through the final thing on the hydrogen storage. We have been also looking at onboard hydrogen storage. And for that, we are looking at metal organic framework and magnesium as two very important materials. But each of them has a problem. Metal organic framework is a physisorption, and magnesium has a chemisorption problem. So this is very, very small binding energy. This is very large binding energy. So we need material between chemisorption and physisorption. So typically, neither of them too. So we need a binding which is neither too strong, not too weak, because dehydrogenation also has to take place. So typically, people think it's a 15 to 30 kilojoules per mole will work better. But what is important is the dehydrogenation kinetics. It is not just the binding energy. It must pull out hydrogen very quickly. So, for example, many people talk of ammonia borane as a very good source of hydrogen. The problem with ammonia borane is that the hydrogens are bound too strong. It's a chemical bond. So when you require the hydrogen, it's very difficult to get them. So can you go to the next slide? So, of course, if you have renewable hydrogen, you can give to cars some application. Can you just go to the next slide? And of course, photosynthesis, that's, you can do artificial photosynthesis. Just 1 minute, just 1 minute. Hello? Yeah, I will enter the 10 minutes. Yeah, I'm sorry that I'm just in between several meetings. So I have another meeting because this got delayed. All right. So what? So can you then go to the next slide? And then light emitting diode. I think I just wanted to tell you how material science has benefited from doping. If you look at doping, they make it better conductors. So silicon, for example, is not a good conductor, but as soon as you put group 3 or group 5 element, they become very good. So in fact, all the LEDs that you see are basically from the silicon, but doped silicon. Can you go to the next slide? The nanomaterials, of course, a lot of possibilities in nanomaterials in terms of catalysis. And of course, this very famous statement of Feynman. But the important thing about nanomaterials to recognize that it is electron microscopy and the fullerenes, which are actually the cornerstone of the nanomaterials. The discovery of nanomaterials. Along with a lot of physics-based theoretical chemistry, I must also mention today that the computational chemistry is evolving, just like when artificial intelligence and machine learning, that is benefiting an area called the informatics. It's called chemoinformatics or bioinformatics. In fact, in drug discovery, a lot of informatics is being used and not necessarily.
Yeah, actually, it's a network problem.
Is it? Okay. So, okay, fine. I'm almost finished. But let me just quickly tell that what I wanted to say that in our group, we have been working on several problems. What I showed you today is very small problems of materials, metal clusters, and hydrogen storage. But basically, we are working on different problems. And I wanted to show just one slide. If that slide can be found out here. Yeah, so can you go to the next slide? We'll quickly go to the run to the slides. I've already told the philosophy of informatics. So can you go to the next slide? Next slide.
Yeah. So
next slide.
Which one?
Yeah, go ahead.
Yeah.
So these are all I have already talked about. Next slide. Yeah. So just wait here. So basically, I think I will end with this slide. That in my research group, I'm working actually on various problems. So what I today showed you is only one, metals and doped metals with hydrogen storage. I also looked at metals as a catalysis, activation, bond activation. But if you look at our work, we are working on electronic structure of molecules, structure and spectra of confined systems, descriptors. We have done a lot of work for the reactivity, like Fukui functions, local softness, and so on, to identify reactivity. We are, of course, working on truly many-body coupled cluster method, which is mentioned, and that is where I started my research, and I have continued, particularly the multi-configuration coupled cluster, to take care of strong and weak correlation both. We have also worked on non-iterative approximation of density functional response, and proposed a new principle, just like principle of maximum hardness. We have proposed a principle of minimum magnetizability for the stability of the systems. We worked a lot on other catalysts, apart from metal clusters that I showed, tin, beta zeolite, and we had also worked on metal aromaticity and anti-aromatic compounds that are purely metal. This is very fascinating, actually, this part, because aromaticity is known to be an organic system like benzene. We have shown that purely metallic systems can also be aromatic or anti-aromatic. So I think there are many research areas I am working, but my major work has been on the development of electronic theories for electronic structure of molecules using the coupled cluster methods. Of course, that is on the heart. And then I would say descriptors, very old days, and very recently I'm working on lots of materials application as well. So along with this, can you come to the next slide? I have particularly on the coupled cluster, that's okay. Now particularly with the coupled cluster, I must say very recently, we have been developing very important work on relativistic coupled cluster. I must tell you again, it's quite technical, because the coupled cluster that we normally did initially was a non-relativistic. But as you know, for heavy atom, like even gold and silver, aluminum, if you want to do a good coupled cluster, you require relativistic. So the calculation that I showed under DFT for all the gold clusters and so on were actually relativistic DFT. I must mention this. So similarly, here we have done relativistic coupled cluster. There it is development that are required. So if you look at many of our papers in Physical Review and Journal of Chemical Physics, in fact, just yesterday we got one paper in JCP on relativistic coupled cluster. So many of the interesting things we are doing for last 5-6 years. There is another very interesting areas where we have been very active. In fact, just now I'm writing a feature article which actually tells the bound state methods for resonance and decay problem. Many of you know in the physics, the resonance and decay problems are very important. But the problem with the resonance state is that they are not square integrable. So they actually go very fast. So you can't use, they do not go very fast. They don't decay very fast. So you can't use bound state methods. The bound state methods have to be square integrable, normalizable functions. But what is interesting is that if you add a complex potential to the Hamiltonian or do a complex scaling, then most of the bound state methods can be used to trap the resonance and decay state, the resonance energies as well as the width. We have done the CAP coupled cluster method. Again, for the first time, we have been working on the complex absorbing potential based coupled cluster methods to identify resonance as well as decay states. We have a lot of work in last maybe 10 years, going back I think I published the first paper in 2005 in Journal of Chemical Physics. I did not mention any of these because it's too technical and each of them would require a separate lectures, of course. So each of my theme would require a separate lecture. So I think with this, I will thank the North Bengal University for inviting me. There is some acknowledgement of some of the sources from where I have taken about chemical education and knowledge. Go to the next slide. Go to the next slide. Yes, I'm thanking to all the funding agencies of SERB, DST, Indo-European, CSIR, Indo-French, etc. And many of my colleagues and collaborators and students from NCL, IIT Bombay, IISA Kolkata, where I stayed, and also from Dr. Avsare from SP College Pune, who has been collaborating with me on the catalyst design. With this, I thank all of you for your attention. Thank you very much.
Thank you, Professor Paul, for such a wonderful lecture. You have took time between your busy schedule. Now, the house is open for question or any comments. Yeah, I think Professor Paul will be happy to take a couple of quick questions. Okay, sir. I have one I want to seek one clarification. How about the fragmentation methods?
Yeah. So a lot of people. I am not working on fragmentation method, but there are a lot of people who are working on fragmentation method. I think it's very important. Yeah, it's very important because for large systems, yes.
Yeah, it can work. And you are talking about the gold clusters. So we have some recent experience in working with small gold clusters which are already synthesized, AU14 clusters. So they are found to be very effective in even visualization process. That's what we predict because it can form very good combination, at least bionano conjugate with retinol, and can help for the transition at higher wavelength.
Yeah, I'm sure. Yeah, because AU14 is also very interesting to know that AU14 is the first non-planar cluster.
Yeah, it's non-planar. Then there are three possible geometries. You have worked out one particular symmetry. That is deep 2H symmetry. That's particularly very effective.
Up to AU13 is planar.
Yeah.
But that comes only if you do relativistic.
Yeah.
No. Without relativity, you don't get. I hope you are using relativistic DFT, right?
Yeah.
Okay.
We have tried to do that. Yeah.
Okay. Yeah. I have not worked on AU14. I worked on AU6, AU8, AU18.
Yeah, AU18 you mostly mentioned, yeah. But AU14 we found it's quite interesting. If that comes out, we are in communication process, I'll send you a copy. Yeah.
Okay, thank you.
Yeah, thank you. Anything else? Anything else? Okay, I think if not, then we'll thank Professor Paul again and request him to come here once again once the situation normalizes. Sir.
Yeah, we are. Yeah, I'm not even sure that the CRSI meeting in February, IIT Guwahati, what will happen?
Yeah. I mean, by now I had been in your place at least more than once.
Yeah, sure.
Yeah.
If many of you, I will meet if the CRSI meeting takes place in IIT Guwahati physically. in February.
Yeah, yes, we are waiting, sir. Yeah.
So let us see what happens. Okay. Yeah, I
Okay.
mean, it's a very uncertain time, but let me thank you again for
Yeah.
coming to the webinar because I have too many things today.
Yeah,
But,
I know.
I'm very happy. I'm very happy to join.
Yeah, you made it perfectly. Thank you, sir.
Yeah. Thank you. Thank you very much.
Thank you.
Thank you. Thank you. Bye. Bye. I'm leaving now for another meeting. Yeah. Thank you.
I know that. Yeah.
Bye.
Thank you, sir. With this, we end our first technical session. The speaker of our next technical session is Dr. Jongkun Im, Associate Professor, Soonchungyang University, South Korea. The session will be chaired by Professor Dilip Kumar Maiti, Department of Chemistry, University of Calcutta. It is a great privilege to introduce our eminent guest and session chair, Professor Dilip Kumar Maiti. He has done his bachelor's in chemistry from Ramakrishna Mission Vidya Mandir, Belur in 1991. He did master's with organic chemistry major from Calcutta University in 1993. Professor Maiti obtained his PhD degree in synthetic organic chemistry from Indian Institute of Chemical Biology 1998. He has done his postdoctoral studies at the School of Medicine, Wayne State University, USA. He has been awarded as the Fellow of Royal Society of Chemistry by RSC London. He is the Associate Editor in the Scientific Reports of Nature Publishing Group and Editorial Board Member in 17 international journals. Professor Maiti has published 115 scientific papers and successfully guided 75 research scholars. Not just in academia, but he has left his mark in industrial sector also. He joined the R&D of SIBA India Private Limited as scientist in 1998 and later moved to RPG Life Science Limited as senior scientist of R&D. He is currently a professor in the Department of Chemistry, University of Calcutta. May I now humbly request Professor D.K. Maiti to kindly chair our second technical session. Please, sir.
Thank you, Mohan. Very good morning. I'm thanking you for inviting me to chair a session. Let me introduce Professor Jongkun Im. He is associate professor currently in the Department of Chemical Engineering, Soonchungyang University. He did BSc and PhD from the Post-Tech, received awards, honors, and several awards, including gold medal from Samsung, Best Teaching Award from Post-Tech, and he is the member of American Chemical Society, Korean Chemical Society, Polymer Society of Korea, Korean Institute of Chemical Engineering. He has published several international papers in international journals. Most importantly, he has several patents in his credit. He has a wide research interest, including synthesis of drugs, proteins, polymers, molecular transporters, enzyme inhibitors, fabrication of nanomaterials like organic, inorganic composites or sensors, conductors, nanofibers, super hydrophobic materials. Today he is going to talk on cell membrane permeable molecular transporters. With these few words, I request Professor Im to deliver his talk. Professor Im, please.
Yes. Hello. Okay.
Yeah.
Thank you for introducing me. So I'm very my name is Professor Jongkun Im, and I'm very happy to join this meeting. And okay, I will first share my screen. Yes, so okay, so can you see this my
No.
PowerPoint slides? No. What's wrong?
Just go for presentations.
Let me try again. Okay. sharing the screen is not working. Let me see. I'm trying again. Present now and entire screen.
Just go to the full screen mode. Yes.
Can you see?
Yeah. It's working.
Okay. Okay. Today, I want to talk about synthetic and application studies of cell membrane permeable molecular transporters. My talk consists of 4 chapters. So first, I will talk about general introduction of molecular transporters. Yes, so in the left figure, this is the plasma membrane. Yeah, the plasma membrane is a lipid bilayer. So many big size macromolecules or charged molecules cannot pass through the cell membrane. Only non-charged molecules or water molecules can pass through the cell membrane. And sometimes nutrients such as glucose or vitamins can pass through the membranes. If you see the right figure, hydrophobic molecules such as gas molecules, oxygen or carbon dioxide can pass the cell membrane. Yes, and sometimes water or small uncharged polar molecules can pass. But large or uncharged polar molecules cannot pass the membranes. But glucose is a energy source of our human body. So sometimes glucose can pass and penetrate into the cells if there's a special particular glucose transporter. And ions are charged, so they cannot pass the cell membranes. They can pass only when there's an ion channel present in the cell membrane. So nanoparticles or some drugs with high molecular weight cannot penetrate into the cells. So drug delivery vector is required to deliver some macromolecules and charged molecules. So people found out a TAT protein was cell membrane permeable. Usually proteins are very big size, so they cannot penetrate into the cells, but especially TAT protein was internalized into the cells, and they can TAT protein can stay in the cytosol. So people try to find out the transmembrane domain, and it was discovered that the basic reason in the HIV-1 TAT protein was essential for cell membrane permeability, and this is the amino acid sequence. So if you see here, there are lysines and arginines. So we can say the cationic amino acids are very important for cell membrane permeability. And among them, arginine is the most important. So if you see here, this is the arginine structure. And at the terminal, there is a guanidine group. And this guanidine group is essential for cell membrane permeability. So many people discovered or developed many cell-penetrating peptides in CPP in abbreviation. So if you see this table, the name of the CPP is penetrating, and this is the sequence. So penetrating peptide or MAP, arginine, MPG, transportan, these are very popular CPPs. And some of them are derived from proteins, or some CPPs are just artificially prepared by people. Yeah, or designed CPPs are here. So the CPPs first interacts with many biomolecules on the cell surface. So on the cell surface, there are phosphates or sulfates and carboxylates. All of them have negative charges. So if this is the CPP, as I said before, the guanidine groups of the arginine is very important. So if you see here, this is the guanidine groups. So the guanidine groups can interact with phosphate groups like this by electrostatic interaction and hydrogen bonding. So there's a weak association between CPP and the cell surface molecules. So after this initial association, the CPP can be internalized into the cells by endocytosis or passive diffusion. Of the CPP uptake. Associated with CPPs. First, CPPs are very unstable in human body or in serum because there are many endogenous proteases in human body. So CPP will be easily degraded by the proteases. So there are also in vivo applicability or selectivity issues, and some CPPs demonstrates cytotoxicity, and the cost of processing or preparation cost is very high. So there are some economic issues, and there's also IP right issues. So from this natural inspiration, guanidinium-rich molecular transporter appeared. So many people developed this guanidine-rich molecular transporter. So if you see this next slide, so as I said, the guanidine group can interact with phosphate groups or sulfate carboxylate groups on cell surface by electrostatic interaction or hydrogen bonding. So with this interaction, this R is just organic molecule. So this organic molecule will gain cell membrane permeability and drug delivery capability. So many people are now preparing or developing molecular transporters. This is not a peptide. It's just a small molecule. It's a molecule. So if you see here, publications regarding CPP and molecular carriers are very much increasing. So this figure shows the timeline of the molecular transporters with diverse backbone. So if you see here in 2000, the backbone is peptide or peptoid, and the guanidiniums exist as a side chain. Next, carbamate and beta peptides were used as a backbone, and guanidiniums exist like here. And dendrimer type or polymers were also used. Nucleic acid was also used. And finally, in 2009, carbohydrate-based molecular transporters were reported. I think this carbohydrate was reported very late because carbohydrate chemistry is usually very difficult. So in my group, I developed and prepared many molecular transporters, and this figure shows the design features. So the scaffold was usually used carbohydrate. I used carbohydrate because it is usually very cheap and it is very safe to human. So once this molecular transporter is in human body, after the metabolism, carbohydrate will not give any harmful effect to human because it's very safe and it's safe. And carbohydrate has usually many hydroxyl groups. So many linkers or many cargoes or drugs can be conjugated to scaffold easily. The linker was linear or branched, and guanidiniums exist at the terminal position. So multiple guanidiniums were attached, and X and Y are cargo, such as drugs or probes like fluorescence tag or targeting ligand can be attached to the scaffold. This is one of the example of the molecular transporter. So here, a linear carbohydrate was used as a scaffold, and the linker was a branch type. And the red color indicates the guanidiniums. So if you see here, totally 8 guanidiniums were attached to the scaffold. And to this R group can be a drug or a probe. Next, I will talk about the general introduction of blood-brain barrier. So in human brain, blood-brain barrier, BBB, exists in the blood capillary. So BBB consists of many epithelial cells in brain. BBB was first discovered in 1880s when an organic dye was injected to a mouse body. The dye can stain all the human organ except brain because of the circulation of the blood. It can stain all the body except brain. When the organic dye was injected to brain, only the brain was stained. This demonstrates that something is covering or protecting the brain. So that indicates the BBB. This figure compares between general capillary and brain capillary. So general capillary is leaky comparing to brain capillary. So if you see here fenestra or cleft means there is a hole. So many nutrients or pathogens or cells, viruses, bacteria can pass through these holes. So it's very leaky. In contrast, brain capillary is very tight. So there's a tight junction. So only limited molecules can pass through this brain capillary. If we see this brain BBB structure of the BBB more carefully, so if we magnify this region, this between endothelial cells, this part is the tight junction. So by several proteins, it's blocked. So many pathogens or such as viruses or lethal bacteria cannot penetrate into the brain. So brain is very protected. The BBB works like a protecting covering. But the bad thing is once the brain is in disease, it's very difficult to treat the disease because many useful drugs can also cannot pass to the brain. Also, there are many efflux pumps on the BBB. So, yeah, in addition to the tight junction, this figure shows the efflux pumps. So this is the luminal. Luminal means this is the blood, and this is the brain region. So many drugs cannot pass and enter the brain because of these efflux pumps. Once the drug or molecule binds to these efflux pumps, it is ejected. So among these efflux pumps, P-glycoprotein is the most well-studied efflux pump. So if we see this table, this table shows the substrates of the efflux pumps in the brain. So the red box shows the P-glycoprotein, and this box shows doxorubicin, paclitaxel. They are very popular drugs used in medicinal chemistry. Also, cisplatin is an anti-cancer agent. AGT is an anti-HIV drug. So all of these drugs are the substrate of the efflux pumps, so they cannot enter the brain. So there is a failure in drug development. It is said that there is a high rate of drug development failure because of bioavailability and efficacy problem. And the major reason involves poor cellular uptake and tissue penetration. Essentially, all the large molecule pharmaceutics cannot cross the BBB. And more than 98% of all small molecules do not cross the BBB either. So many promising drug candidates or lead compounds are failed in the drug development because of the BBB. So it's very difficult to treat the disease in the brain. So we can say the drug development for the treatment of central nervous
System.
disease. Nervous system disease is very difficult. Next, I will talk about BBB permeable AGT derivatives. So this is the work of my research work. So it is said in AIDS patients, there is a brain tissue loss. Actually, AIDS can be cured nowadays, but once the HIV enters the brain, it's very difficult to treat or eradicate the HIV because many useful anti-HIV drugs cannot penetrate to the brain. So once the brain is infected by HIV, it's impossible to treat the disease. So many AIDS patients could die. AGT is one of the most popular drugs in anti-HIV drugs. So this is the structure of AGT. AGT is the abbreviation of azithromycin. So once AGT is in cell, it is metabolized. So by phosphorylation. So the AGT will get triphosphate like this, and in the reverse transcriptase is a enzyme in HIV. So from this viral RNA, DNA can be prepared by this enzyme by the virus in the virus. But AGT is a derivative of thymine. So AGT can bind to this DNA replication. So it's blocked from this point. So by this mechanism, virus cannot be duplicated. So virus replication will be inhibited by this mechanism. But the problem is brain concentration of AGT is extremely low because of the BBB and the efflux system. So the AGT drug cannot enter the brain. So my objective was to prepare BBB permeable AGT derivative. So if you see here, the scaffold was the carbohydrate, and this carbohydrate is called sorbitol. And at the terminal, there's guanidiniums, and R1 is FITC. This is a fluorescence tag for imaging by microscope. And the drug AGT is conjugated at R2 position. So first, I prepared the guanidylating agent like this. So it has N-triflate is very good leaving group. So this can make guanidiniums. And this number 7 is the branched linker. And to conjugate the drug AGT to the scaffold, I use succinic anhydride to make like succinic acid. So this carboxylic acid can be conjugated to the sugar. I will skip the synthesis part, just I will talk briefly. So starting from alpha D glucose, it was reduced to a linear sorbitol structure by selectively protecting the hydroxyl groups. I could get AGT molecular transporter. So here, R2 indicates this guanidiniums. There were 8 guanidiniums, and FITC was conjugated here, and R1 is the AGT drug. So if you see the structure, all the linkers and the drugs are conjugated by ester bonds, because the drugs or the molecular transport itself should be degraded inside cells, and the drug should be easily released inside cells. So ester bonds can be easily hydrolyzed by diverse enzymes such as esterases in cells. So I always conjugated or made the bond by ester bonds instead of robust amide bonds. So I took the UV visible spectrum. So this peak comes from the AGT drug and FITC. And this peak comes from the AGT drug. So the AGT-MT was incubated in HeLa cells for 30 minutes. And after washing, I observed the fluorescence by confocal microscopy. So this is the cell structure. So we can say the green fluorescence appears in the cytoplasm mostly. So I assume that uptake mechanism might be passive diffusion. Also, the cells were co-incubated with mitotracker, lysotracker, rhodamine B dextran. Mitotracker stains, all of them are commercial agents. So mitotracker stains selectively mitochondria. Lysotracker stains lysosomes. And this rhodamine B dextran is endosome marker. So when I co-incubated them, I could see that the molecular transporter has high affinity toward mitochondria, because if we see this green and red signal according to this line, both signals match very well. So the conclusion is that AGT-MT has high affinity toward mitochondria rather than lysosome or endosomes. So then after that, the molecular transporter was injected to a mouse to the peritoneal region. So the mouse was sacrificed and each organ was observed. And we can see the control is just the buffer solution. So we can see the green fluorescence from the brain. This indicates that the AGTMT can cross the BBB and enter the brain. So we hope that this AGT drug can be delivered to the brain. Next, I will talk about transdermal delivery of proteins via molecular transporters. So there is an association between protein and carriers in non-covalent manner. This green structure is green fluorescence protein. This protein can show fluorescence, green fluorescence by itself. It has net charge -8, and the PI isoelectric point is 5.8. So in physiological condition, the pH will be 7. So the GFP will have negative charges. So the surface is too negative to cross the cell membrane. The protein normally the protein has bigger size and it has some charges. So almost all the proteins cannot cross the cell membrane. But if we mix the GFP with our molecular carriers, a complex can be formed. A protein molecular carrier complex can be made because molecular carriers have positive charges, but the protein surface has negative charges. So through the electrostatic interactions, several molecular carriers can bind to the GFP through non-covalent interactions. So GFP was used as a model cargo. So after making this complex was applied to the skin, mouse skin. And I tried to observe the green fluorescence coming from the GFP. This figure shows the structure of the dry skin. So usually skin has 3 layers. They are epidermis, dermis, and hypodermis. Epidermis is almost a dead skin. There's no cellular metabolism in the epidermis layer. And in the dermis layer, yes, there are some capillaries here, and there are many useful proteins such as collagen or fibroblasts. Yes. So again, I synthesized the molecular carriers. So starting from this desorbitor, using these trityl groups, it was only the primary alcohol parts groups were protected. And then I did a peracylation with these linkers, guanidinium box. After that, with the acidic condition, remove the trityl groups and all the Bach groups, giving this guanidinium hydrochloride. So yeah, I could get these guanidiniums so I can say, because there are 8 guanidines, so I can call this molecule sorbitor G8. So sorbitor G8 was mixed with GFP, and I observed the cellular uptake by chemical microscopy. So here the complex was made with different molar ratio, 1:0, 1:5 to 1:60. So GFP is 1 and sorbitor G8 was 0, 5, 10, 20, 40, 60 ratio. So figure A shows 1:0, which means GFP only. So as I said, GFP is very big, has a big size, so they never cross the cell membrane. So there was no fluorescence. From 1 to 5 ratio, we can see a dim fluorescence, and the brightest fluorescence reached at 1 to 40 ratio, as it can be shown in figure E. Next, the GFP molecular carrier complex was applied to a mouse skin. So the solution was dropped on the skin of the abdomen, and after 3 hours, the skin was dissected and observed by 2-photon microscopy. Collagen was also observed by just a reference. Collagen, is a protein for elasticity in skin. So I observed the green fluorescence. So like this, I can see the green fluorescence coming from GFP. So I can say, these results demonstrates that GFP is delivered to 63 more than 63 micrometer depth. So GFP was able to be delivered to hypodermis area. I also tried with different proteins such as albumin, FITC, concanavalin A, FITC, immunoglobulin G, FITC. Albumin, con A, immunoglobulin G are not fluorescent, so FITC was attached. And they have different molecular weight, as you can see here. Or if you see this table, molecular weight of each protein is different, and the diameter or the size are all different. So I made the complexes and I observed the depth, the fluorescence according to the depth. So GFP reached 105 micrometer, and also if you see this figure, I also tried with arginine octamer. This arginine octamer is a peptide, CPP, and it has also 8 guanidines. So the white bar is the highest. So this indicates that my compound, sorbitol G8, has higher efficiency than the CPP for transdermal delivery of proteins. So this is the anatomy photo of mouse skin. So I can say the proteins can be delivered to the dermis area. So in the dermis area, there's a capillary. So we can expect that the proteins can be enter the circulating system in the dermis layer. So many useful proteins or therapeutic proteins or antibodies also can apply to skin, and with the help of the molecular transporters, they can enter the circulating system. Okay, in conclusion, I prepare several types of carbohydrate-based molecular transporters, and many kinds of drugs or cargos were conjugated to the molecular transporters, and all of them worked well as a delivery vector than the drug alone. Scaffold was carbohydrates such as sorbitol or trehalose. When trehalose was used, it is reported that trehalose can alleviate the Huntington's disease. And linkers was used, and the cargos was FITC, and many kinds of drugs were conjugated. AGT for AIDS, 5-fluorouracil, and CPT for brain or colon cancer. Ibuprofen as an anti-inflammatory drug was also conjugated. yeah, people take ibuprofen for pain relief, yes, but it was reported that if ibuprofen is taken up for a long term, it can also alleviate or slow down AD. AD is Alzheimer's disease and PD is Parkinson's disease. Yes. So if ibuprofen can be delivered to brain, it can help the alleviation of AD and PD. And geldanomycin is an antibiotic. Proteins, GFP or other FIT-stack proteins were also delivered transdermally, and nanoparticles were also conjugated. I didn't say about this because of the time limitation, yes, but I also conjugated quantum dots, and they were delivered to brains. G is usually guanidines, and I'm also trying to use creatines. Creatines is a natural product, so I hope these creatines can reduce the cytotoxicity of the molecular transporter. So yeah, I'm collaborating with several groups. I'm much grateful to them. Yeah, these are the lab member list. And yeah, thank you for your attention.
Thank you, Professor Im, for your illuminating talk. Now the talk is open for discussion. Please unmute your phone, and if you have any query, please ask. Hello?
Yes?
Okay, Professor Im, suppose you design a drug and it is not transported to the brain. So that time, what precaution you take, or what type of thing you do to transport it to the to cross the blood-brain barrier?
Yes. So usually, as I said, yeah, essentially large molecule drugs cannot cross the BBB, and almost 98 all small molecules cannot cross the BBB. So yeah, we can assume almost all kinds of drugs, doxorubicin, Taxol, or cisplatin, and many kinds of drugs cannot enter the brain. So what I did is I prepared this molecular transporter and conjugated the drug. So with the help of this molecular transporter, the drug could enter the brain. So first I did the cellular uptake experiments, and also the AGT drug conjugate was applied to administered to a mouse, and I could see the drug enter the brain. Yes, this is my answer.
Yeah. Okay, thank you.
Yeah,
And,
So, sir, I have one question, sir.
Okay, go ahead.
Is there any standard value of the blood-brain barrier for a potential drug or drug candidate? Can you suggest me? Because I'm working in a computational drug design, that's why this value is needed for me. If you guide me.
Can you say your question again?
Oh, is there any standard value of the blood-brain barrier of a potential drug which will penetrate into the brain?
Yeah. So,
can you hear me, sir?
Yeah. So for a drug to pass the BBB, the drug should be very low molecular weight, and the drug should be lipophilic. It should not be hydrophilic. Yeah.
Okay.
And there will be no
value, any parameter?
There will be a parameter. Standard parameters. There is a rule. So
Okay.
I don't remember the exact parameters or the exact standard value, but
Okay.
yeah, maybe you can easily search the parameters or
I
standard.
could not find this standard value. That's why I'm asking you. I could not find this standard value. That's why. Okay, if you just
exactly, yeah.
fine, you can. I can ask.
Yeah, right. Okay.
Okay, next question, please.
Yeah, I have one query. Does such carriers reduce the activity of the drug or it keeps the activity of the drug intact? Because you are tagging the molecule with a carrier. So does it reduce the efficacy of the drug or does it?
Are you asking if the drug efficacy is reduced?
Yeah.
Okay, so when I studied with this 5-fluorouracil or chemotherapy drugs, they are anti-cancer agents. So I incubated the molecular transporters with cancer cells, and I observed that the cell viability of cancer cells are much reduced. So that shows that the anti-cancer drugs are well delivered into the cells, and that means the drug works well as a anti-cancer agent. Yeah, actually the drug is not modified. It's just conjugated. So once the drug is released inside cells, it will obviously work because the drug efficacy is already well known and well studied.
Okay, thank you.
Okay, yes.
Anyone? Okay. As there is no more question, let's thank Professor Im for his nice talk. Now I'll go back to Moa. Moa, please.
Thank you so much, sir. That was a really very interesting lecture. Now, moving forward, we have completed our second technical session. So, due to the unfortunate absence of our Honorable Vice Chancellor and Chief Guest, Dr. Subiresh Bhattacharya, University of North Bengal, we will skip the valedictory session, which was supposed to be enriched with a song sung by our Honorable VC sir. So, I guess we are not that lucky today. Anyhow, as we have reached the end of our seminar, I may now request Dr. Shudra Rana, Assistant Professor, Department of Chemistry, University of North Bengal, and also one of the convener of today's international seminar, to kindly propose the vote of thanks. Please, sir.
Okay, thank you, Mohua. So, am I audible?
Yes, sir.
Yeah. Okay. Honorable Vice Chancellor, Dr. Subiresh Bhattacharya, Professor Anirban Mishra, Chairman of the seminar, also Head of the Department of Chemistry, Professor Pranab Ghosh, Convener of the CRSA, North Bengal Local Chapter, respected Professor M.N. Roy, dear colleagues, dignitaries, eminent speaker, chairpersons, and all the participants. A very good morning to all of you. So firstly, I express my sincere thanks and gratitude to our Honorable Vice Chancellor, Sir, for his encouragement in order to arrange this seminar. I convey my best regards and thanks to Professor Saurabh Pal for his valuable deliberation on research advances in computational chemistry in spite of his busy schedule. It was indeed an insightful talk for all of us. I extend my earnest thanks to Professor J. Im for delivering an exciting lecture on cell-permeable molecular transporter. It was indeed a helpful discussion for all the audience. In this connection, I express my thanks and regards to Professor D.K. Maiti from University of Calcutta for giving his valuable time to share the technical session of today's seminar. Thank you, sir. I must thank Computer Center for their wholehearted support for arranging this seminar. I also want to thank my dear colleague, Dr. Sajal Das, for his help and support to arrange this seminar. And at last, I thank all the participants across the country for making this seminar a success, because without their participation, it is not possible to conduct a seminar. At last, thank you all.
Again, thank you one and all for joining with us today and patiently hearing all of the enlightening lecture. I now humbly ask the permission of Professor Anirban Mishra, Head, Department of Chemistry, University of North Bengal, to end this virtual one-day seminar. Please, sir.
I once again, my sincere thanks goes to the organizers, the today's convener, and all my dear colleagues, and the North Bengal Local Chapter CRSI, convener of North Bengal Local Chapter CRSI, Professor Pranab Ghosh, and our Honorable Vice Chancellor, Dr. Shubhresh Bhattacharya, and eminent speakers, Professor Saurabh Pal and me, and also our chairperson, Professor Maiti, and all the delegates and those who are present. I thank you all. And with this, I think it's time to close it and see you in some other event next time. Thank you very much.
Thank you, sir.
Thank you. Thank you for your support. Actually, laptop